last week we started the 3.25 and we didn't manage to finish. Did anyone try to finish at home and manage to get the same answers that we have here? Okay, so what we had for the 3.25? We had a system where we had a double pane window where we had glass in both sides and we had air in between those sides, okay? We knew the dimensions and we are asked to dictate convection heat transfer coefficients as being those ones. Determine the steady rate of heat transfer through this double pane window. So here is what they're asking us. Find the steady rate of heat transfer through this double pane window and the temperature of its inner surface, so the temperature in the inside, when the room is maintained at 24 degrees Celsius, while the temperature of the outdoors is -5 degrees Celsius. So what we did so far, we built our thermal resistance system where we realized that we have convection heat transfer between the air in the outer surface, the air outside in the inner surface and the glass. We have conduction in the wall of the glass in both sides. We have conduction between the glass and the air because my air is stagnant, so it acts like a conducting medium. And we have another convection between the outer surface and the air in the outer side of the surface, okay? So this is our thermal contact resistance. And our main goal here is to find our Q. So to find our Q, we concluded that first we should find each one of the resistances and the total resistance of our system. We know that our steady rate of heat transfer through the glass is going to be Q is equal my temperature in the inner side minus my temperature in the outer side divided by my total resistances. My resistances are in parallel or in series? Series or parallel, what do I have here? You can participate. Series, exactly, Connor. So my system here has resistance in series. If I have a system with resistance in series, my total resistance is going to be the sum of all the resistances. Resistance 1 plus resistance 2 plus resistance 3 and so on. Okay? This is what we need to know to solve this problem. So let's find each one of our resistances. We know that resistances 1 and 3. So my resistances through the glass are the same, resistance 1 and 3, because I have the same thickness of glass in both sides with the same composition of glass with the same conductivity. Let's calculate each one of those resistances then. I'm going to start here with Ri. 1 divided by my age of convection between the glass in the inner side. So it's 10 watts per meter square multiplied by my area of the glass. My area of the glass, did we calculate before? No, we didn't. So I'm going to calculate the area here so we can use for other things as well. So my area, I'm given the dimensions of the glass. My glass is area. My glass has the dimensions of 1.2 meters by 2 meters. So my area of my heat transfer is through a glass window of 2.4 meters square. So this is the dimension is going to be, the area is going to be used in all my systems, in all my resistances is this area here. Okay. I'm giving here the sizes of my window. So 10 watts per meter square multiplied by 2.4 meters square. Meter square cancels with meters square. So my convection resistance is going to be 0. I'm missing a unit here, meter square degrees Celsius, okay? I forgot the degrees Celsius in there. My convection resistance between the inner side and the glass is going to be 0.04167 degrees Celsius per watts. Okay, so that's the resistance I between my inner side, the air in the inner side, and my glass. Now I'm going to find the conduction resistances, R1 and R3, okay? Remember that they are the same. So my conduction resistance is going to be L1, that's the thickness of my glass. I know the thickness is 3 millimeters, so 0.003 meters, divided by my conductivity of the glass, that's given in the problem as well. That's 0.78 watts per meter degrees Celsius. Multiplied by the area, that is 2.4 meters square. Meter cancels with meters. So my resistance is going to be 0.00160 degrees Celsius per watts. I have my resistances 1 and 3. Now I'm going to find my resistance 2. That is my resistance between these panels and the air. So it's this resistance to the conductivity of the heat inside this stagnant air. Remember that I have stagnant air, so it's acting like a solid in this case. So my thickness would be the distance between those two panels here. That's a 12 millimeters wide stagnant airspace. So this is going to be 0.012 meters divided by my K of the air, that's 0.026 watts per meter degrees Celsius multiplied by my area, 2.4 meters square. So my resistance in this case is going to be 0.19231 degrees Celsius per watts. The meters cancel with each other. And my last resistance is due to convection between my outer wall and the air in the outer side. I have a convection resistance, 1 divided by age of convection, 25 watts per meter squared degrees Celsius multiplied by 2.4 meters square. So my last resistance is 0.01667 degrees Celsius per watts. Well, what I'm looking for here, I'm looking for my total resistances. So the total resistance for a series of resistances is going to be my resistance of convection, 1 plus twice my R1, that's R1 plus R3, okay? Or I can even put here R1 plus R3, plus my resistance 2, plus my convection resistance in the outer side. So the sum of all the resistance that we calculated so far. So 0.0417 plus 167. I forgot a 6 here. 4167 plus 0.00160 plus 60 because they are the same R1 and R3 plus 0.19231 plus 0.01667. So my total resistance is going to be 0.25 385 degrees Celsius per watts. So this is my total resistance between the inside of my house and the outside of my house caused by this window, inside and outside of the window. What is our goal here for now is to find my steady state rate of heat transfer through my glass window. So my steady state heat transfer is going to be temperature of the inside minus temperature of the outer side divided by my total resistance. So I have here 24 degrees Celsius minus 5, that was the temperature, divided by 0.25385 degrees Celsius per watts. I cancel the degrees Celsius. So my steady rate of heat transfer is going to be 114 watts. Did anyone get the same answer when solving on yourself by your own? Next, they ask as well to find the temperature of the inner surface. What's the temperature of the inner surface? The temperature of the glass here. Let's call that temperature 1. So they want to know this temperature here. What resistance is involved in here? Just my convection resistance, right? Between this air here and the temperature of the surface here. Okay, so I just have convection between this internal surface and my temperature of the air. So I can use the same idea, but for a convection case. So my steady rate of heat transfer, if I have convection, is equal my temperature of my air minus my temperature of my surface divided by my convection resistance between them. I know the convection resistance, I know my temperature of the air and the rate of heat transfer. I can find my temperature 1. So my temperature 1 is going to be temperature of the air 1 minus rate of heat transfer multiplied by my convection resistance. So my temperature at the glass in the inner side is going to be my temperature of the air, 24 degrees Celsius, minus 114 watts, multiplied by the convection resistance between them. Cancel watts with watts. So my temperature of the glass in the inside is 19.2 degrees Celsius. Okay. Any questions on this one? Let's continuing from last class. Anthony mentioned to me that some people are confused about which book I'm using. Again, it's the 5th edition. I'm going to send the ISBN in here, just so you know exactly which one in case you're trying to find it, okay? So this is the ISBN of the exactly one for the book that I'm using, okay? is the 5th edition. Any questions? You'd have a question number 3.26, okay? That would ask you to find, I'm going to try to copy here. I'm not going to solve this one, I just want you to have an idea how you'd solve, okay? Or to understand the theory behind it. The 3.26 would ask you, repeat the problem 3.25, assuming the space between the two glass layers is evacuated. So assuming that what you have between them is not air, is vacuum. Can I conduct heat through vacuum? Yes or no? No, exactly. I cannot have heat being conducted through vacuum. If I'm considering that there is no radiation,
You are currently the only person in this conference.
the only type of heat transfer that I could have is due to convection. Sorry, due to radiation. So radiation is the only type of heat transfer that I can have through vacuum. The problem, 3.25, tells me to not consider radiation, okay? It tells me to consider that there is no radiation, disregarding heat transfer by radiation. So if I'm disregarding radiation and I have a vacuum, the answer for this problem here is that I cannot have any heat transfer, so that my heat rate would be 0. Okay? That would be my answer to 3.26, that heat cannot be conducted through an evacuated space, since the thermal conductivity of vacuum is 0. So the K for vacuum is 0. So there is no medium to conduct heat. So my thermal resistance would also be 0. Therefore, if we are not considering radiation, the heat transfer through this window, if I have a vacuum, would be 0. Okay? If the problem told you to consider radiation, then you could go ahead and find your resistance due to radiation. I'm not going to do that here. Not a conceptual problem for you to think a little bit, okay? Any questions so far? I'm going to get the next one, the 2.61. Am I going too fast? You know, you have a chat thing that you can answer and I ask something, right? I need feedback as well. Okay. So the next one we're going to be solving is the 3.61, where we have a little bit more involved into this one, and we need to pay attention to understand the problem, okay? Most of the problems with this one is understanding the problem. So I want to build a 10 centimeters thick wall. So I want to have a wall that's 10 centimeters thick. And to build this wall, I'm going to be using 2.5 meters long wood studs. So I'm going to pile a few studs to build this wall. Okay, these studs, they are 2.5 meters long. Okay, let's start taking down data. I'm going to talk first about my studs. They have a length of 2.5 meters. So let's draw the representation of one of them. Two dot 10 centimeters by 10 centimeters. With a K, so my conductivity of this wooden studs is 0.11 watts per meter Kelvin. And they have a cross section of 10 by 10. Oopsie, undo here. This is my cross section of 10 by 10. At some point, the builder ran out of those studs. Instead of using studs and piling up those studs, the builder started to put together pairs of 2.5 meter long wood studs that have a cross section of 5 by 10. So when he ran out of this first one, he started getting studs that were 5 by 10 and nailing them together to get 10 by 10. Now I have 5, 5, 10, and again 2.5. Okay, now he's nailing together pairs of studs. And here are my nails. I'm going to put here my pairs. Here I have studs of 10 by 10. And now I have pairs of 5 by 10 centimeters. But to put them together, he needs to nail those studs, and he's using magnesium steel nails, okay, to put those studs together. These magnesium steel nails they have a K, a conductivity of 50 watts per meter Kelvin. And the nails are 10 centimeters long, so they just go across exactly my 10 centimeter stud. So my L of the nails is 10 centimeter. I know that these nails have a diameter, so the diameter of each one of those nails here, 0.4 centimeters. The diameter of the nails, 0.4 centimeters, 0.004 meter. A total of 50 nails are used to connect two studs. So for each pair of studs, I need 50 nails for the pair, which are mounted to the wall such that the nails cross the wall. So in the first situation, I have studs. In the second situation, I have pairs of studs with the nail going across here, 50 nails across them. The temperature difference between the inner and outer surfaces of the wall, temperature inner, temperature outer. So I'm not given a temperature, I'm given a temperature difference. So I know my delta T between inner and outer surface is 8 degrees Celsius. Assuming the thermal contact resistance between the two layers to be negligible, so the thermal contact resistance between the studs is 0. So I'm assuming that there is no contact resistance between the two wood studs, the 5 centimeters ones. Determine the rate of heat transfer, A to the solid stud. So the letter A, in the first part of the problem, I just want to find my rate of heat transfer through one solid stud, the 10 by 10, okay? Just want the Q passing through here. Well, if I have one solid stud, I can assume one-dimensional heat transfer with the L, with a temperature in the inside and a temperature in the outside. And I consider that I have just one resistance, okay? So I assume that here I have just the resistance of my stud. So the only resistance I have is the resistance due to conduction of one single stud. So I can say that my conduction resistance of one stud, the 10 centimeters by 10, is equal to the thickness of the stud multiplied by my conductivity and the area of this stud. I know that my L, so my thickness is 10 centimeters, so that's 0.1 meters. I'm given the K for the wood stud, 0.11 watts per meter degrees Celsius, multiplied by the area. Which area I'm assuming the area for the heat transfer? Is that this area or this area here? The larger or the smaller area? Which area I'm assuming heat transfer? Exactly, the larger area. My heat is going from this side to this other side, okay? So my area for heat transfer is going to be my 0.1 meters by my 2.5 meters. So my area for the heat transfer is 0.25 meters square, okay? My heat is going from here to the other side. 0.25 meters square. So my resistance of this stud is 3.636 degrees Celsius per watts. What is my relationship between resistance and heat transfer, my heat rate? My heat rate is equal to delta T divided to the resistance of the stud. My delta T, 8 degrees Celsius, divided by 3.636 degrees Celsius per watts. Cancel the degrees Celsius. My heat rate is going to be 2.2 watts. That through a single stud. Okay. The next part of the problem, tell me if I'm going too fast, okay? I don't know how much time you need to copy. The next part of the problem asks me to calculate the heat transfer through a stud pair of equal length and width nailed to each other. So now I want to know what is my heat transfer through this pair here, where I have stud, nail, stud, and I have 50 nails. So now I need to consider the heat transfer through the wood, but also the heat transfer through the nails. So if I looked through that in a one-dimensional approach, what I would see? I would see my stud with my nails going through it. okay? So I have my L, that's again 10 centimeters because I want my pair to be 10 centimeters. I'm not assuming that I have a contact resistance between them, okay? So I don't need to worry about the division between each one of the 5 centimeters, okay? But what I would have is that 5 and 5. I'm not too worried about it. I don't have contact resistance between them. Let's think about that in terms of resistance, okay? I have a temperature 1 in the inner surface, and I have a temperature 2 in the outer surface. Do you think that the resistance of the nails and the wood, they are in series or they are parallel to each other? Would that be a series or a parallel case? Someone's typing. Parallel, exactly, Connor. So I have my resistance of my nails, and I have my resistance of my wood, the wood studs. So here I have a parallel resistance type of problem, okay? First of all, I'm going to start here by calculating what area of this whole system is taken by nails. I have lots of nails here, so let's find out what's the area of my nails. Well, I know that I have 50 nails, and I know that the nails are round, okay? So I know the diameter of these nails, 0.004. Okay, so 50 multiplied by pi d squared divided by 4. So my area of 50 nails is equal to 0.000600 628 meters square. So out of all this side area that I have here, this amount is taken by nails. That's important because I want to know what's my resistance caused by those 50 nails. So how do I calculate my resistance caused by those 50 nails? Is that a convection or a conduction resistance? A conduction, okay? I have a solid there. So my resistance caused by those 50 nails is going to be L divided by K multiplied by the area of the nails. K of the nails. I was told that the nails are 10 centimeters long. So 0.1 meter. I was given the K of the magnesium steel. Manganese, sorry. Manganese steel nails. My K is 50. So I have my K as well, 50 watts per meter degree Celsius. And then now I know the area occupied by all those nails. Okay, so the meters. So my resistance caused by my nails is going to be 3.18 degrees Celsius per watts. Everything all right so far? Any questions? What's the next thing I need to do? Thank you, Dominique. The next thing I need to do is to find my resistance due to my studs, the 5 centimeter ones. Well, together they account for 10 centimeters, so I'm going to omit the fact that each one is 5, okay? So I'm just going to say that the resistance caused by the studs. Again, I have a conduction resistance, L divided by K multiplied by A. I know that these studs account for 10 centimeters together, so 0.1 meters would be the 5 plus 5 centimeters, so 0.1 meters. Divide by my K of the wood is the same wood, so 0.11 watts per meter degrees Celsius. My area now. Do I use the whole area? No, correct? Is my total area of the 2.5 meters long studs minus the area occupied by the nails. Okay. So the total area minus the area occupied by my nails. That's why understanding the problem is really, really important, okay? So you know exactly which area you need to use for your heat transfer. It's not just applying the equations, it's understanding what you are applying and why you are applying it. So my resistance in this case is going to be 3.65 degrees Celsius per watts. And now I can find my total resistance of the combination stud plus nails. So if I have a parallel resistance, the sum of the resistance is equal 1 divided by total resistance equal to 1 divided by resistance of the stud plus 1 divided by resistance of the nails. Have you seen that with Anthony already? 0.25 minus 0.0000628. This two looks weird. Okay. That's this one, Dominic? No problem. That's the area of the nails that we calculated before. So that's going to be 1 divided by 3.65 plus 1 divided by 3.18. So my total resistance is going to be 1.70 degrees Celsius per watt. What I want here, I want my heat transfer, right? So my heat transfer rate is equal to delta T divided by my resistance of the stud combination. 80 degrees Celsius divided by 1.70 degrees Celsius per watt. So my heat transfer is going to be 4.7 watts. Is that higher or lower than what we had with just one single stud? When I calculated for just one single stud without being a combination, my heat rate was 2.2, right? Higher, exactly, Alex and Sunqui. If my heat transfer is higher, does it mean that's a better insulator or a worse insulator? Worse, exactly. So it means that by replacing that, I could be lowering the BER rating of my house. So a simple decision like that of, oh, I don't have enough material, I'm replacing that by that, could be impacting the quality of the home they're building and impacting the BER rating. So how good is the insulation of the house? Just a bit of a discussion in terms of like why as engineers it's so important to understand those concepts. The old thing of just put that's the same. No, it's not the same. Okay. And the last thing they're asking us to calculate is also determine the effective conductivity of the nailed stud pair. So they want to know the effective conductivity, the K effective. I can refer back to my Fourier law for heat transfer. That's Q is equal K, in this case, my effective K, multiplied by my area, delta T divided by L. That's the same equation used in linear conduction, isn't it? I want to find the K effective. Pay attention that when we use the resistance equations, we didn't have the K for the combination. We had the K for each one of them. Now we want to find the K for this combination here, okay? My K for the combination is going to be QL divided by delta T multiplied by my area. My K effective. The Q, the 4.7 watts, multiplied by my L, that's the combined thickness of the two studs, 0.1 meters, divided by my delta T, we know that's the 8 degrees Celsius, multiplied by the area. In this case, because I'm talking about the combination, I'm going to use the total area. Okay, now I want the K effective for the combination. So the combination covers the total 0.25 meters square area. I cancel one of the meters here, so my result is going to be 0.235 watts per meter degrees Celsius. So my conductivity is 0.235. What was the conductivity of using simply a stud? Was 0.11, the K for simply using a wood stud. So it's more than twice the conductivity of using simply one stud. It's more than doubling my conductivity. One thing that you need to be careful as well when you are solving problems in the exam as well, I know that Anthony likes that to ask you to add as well your assumptions, okay? So when you start this problem, you need to state your assumptions. Here we are assuming that your heat transfer is steady, so there is no change with time. We assumed as well that your heat transfer was one-dimensional. We used the one-dimensional in X only. We assumed that the thermal conductivities were constant, so there was no change of conductivity, and that we didn't have thermal contact resistance between the two layers. And we also did not consider radiation, so we disregarded radiation. So those are just some of the assumptions that you can make and you can state when you are doing your exams, okay? I know that Anthony likes if you state your assumptions. Okay, any questions? Okay, perfect. The next one we're going to be solving is the 3.67. Let me know if I'm moving too quick, okay? If you want more time to copy or something like that. Again, I don't know how much time you need to copy things, so. And our systems get more complex. So, 3.67. Have you studied all those things with Anthony already, the resistances? Can someone just confirm to me, please? So, a 4-meter high, 6-meter wide wall. So I have a wall. And this wall is 4 meters high, 6 meters wide, consists of 18 by 30 centimeters cross sections. So 18 by 30 cross section of horizontal bricks. And now it goes about describing this section here, okay? So I know the total side of my wall. Here I'm going to be looking at this section here, small section of this wall and how is that built, okay? So I have bricks, my bricks are 18 centimeter, 0.18 meter by 30 centimeters, 0.30 meters. So that's are the dimensions of my bricks. I have a brick in the center with these dimensions here. And a K, a conductivity of 0.72 watts per meter Kelvin. Next, these bricks are separated by plaster layers. So next thing that it goes about describing is this plaster layers. Okay. I'm just going to change my so I have here plaster layers. All this is plaster. And they give me the thickness of the plaster layers. So my plaster layers are 3 centimeters thick between the bricks. Okay, so to be 3 centimeters between those two bricks. I'm going to take a picture just of a 33 millimeter, 33 centimeter part of the wall, okay, to facilitate my calculations. So I would say that I have plaster 1.5 centimeters above and 1.5 centimeters below each one of my bricks, okay? In a way that my thickness of the plaster is 30 centimeters thick between the bricks. And they give me the K for this plaster. 0.22 watts per meter Kelvin. There are also 2 centimeters thick plaster layers on each side of the wall. So here, between here and here, I have 2 centimeters. And between here and here, I have 2 centimeters. So 3 centimeters between bricks, 2 centimeters between the wall and the brick. Two centimeters between wall and the brick. What else? A 2 centimeter thick ridged foam. So I have another material here. I have foam, plaster bricks and foam. With a K 0.026 watts per meter Kelvin, so a good insulator, on the inner side of the wall. So in here, I have a foam. And this foam is 2 centimeters thick. And now they go about describing the rest of the problem. On the inner side of all, the indoor and outdoor temperatures are 22 degrees Celsius and minus 4 degrees Celsius. So my temperature of the air in the inside is 22 degrees Celsius, and my temperature of the air in the outside is minus 4 degrees Celsius. And the convection heat transfer coefficients in the inner and outer sides are, so I have my convection coefficient in the inside, 10 watts per meter square Kelvin, and my convection coefficient in the outside, inside and outside, 20 watts per meter square Kelvin. Assuming one-dimensional heat transfer and disregarding radiation, so I'm not considering radiation in this problem, determine the rate heat transfer through the wall. So I want to find my rate of heat transfer through the wall. That's my main goal here. Okay, I have a lot of things going on here. I have resistances in parallel, resistances in series. I have so a mixed system here. Okay, the first thing we do when attacking a problem like that is first stating your assumptions. So we are assuming here steady state. I'm going to state the assumptions here. Steady state. What else I'm assuming? One-dimensional conduction and convectional. Always state your assumptions, you know. Anthony loves it. Your thermal conductivities are constant. I don't have thermal conductivities changing. They are constant. And radiation is not considered, so your transfer to radiation is 0. You're disregarding radiation. First thing, get your assumptions. Second thing, build your thermal resistance system, okay? Draw your thermal resistance. Thermal resistances. Draw your schematic, okay? Let's start here and see what we have. Looking at our system. I'm just going to reduce the zoom a little bit. Okay. Let's build our system. I have my temperature of the air in the inside. Okay, so my temperature of the air here. And I have my first thing here, my foam. What heat transfer I have between the air and the foam? So my Ri, I'm going to call here. My Ri, I'm going to say that I have a convection inside. So convection between the air and the wall of the foam. The next resistance I have is my resistance of conduction due to my foam. So my next one, I'm going to call here my resistance 1, my resistance due to the foam. Next, I have a layer of plaster, okay? In this line here, I have just a plaster. So my next one, I'm going to call my resistance 2. It's just my resistance through the plaster. Conduction resistance, conduction resistance. Next thing, what I have some plaster here. I have the brick here, and I have more plaster here. So I have resistances in parallel. So I have now my resistance due to the plaster in the top. I have my resistance of the brick, and I have my resistance to the plaster in the bottom. Okay, I'm going to call that my resistance 3, resistance 4, and resistance 5. Here I have plaster, brick, and the plaster again. Resistances in parallel. And the last, not the last yet, but I have another resistance here to the plaster again. So another conduction resistance. All those are conduction. See? All those resistance here are conduction resistances. My next one is again conduction resistance. I'm going to call here my resistance 6. Is my resistance to the other plaster in the other side. And this conduction again. And finally, I have my last resistance. That is due to my outer and the air. And here I have my temperature of the air in the outside. So this is my resistance 7, going to call resistance with the outer side. That's my convection resistant with my outside. You won't have time to finish that. Make sure to take down those resistances. And the next week, we are going to solve this system. Any questions on that? No questions? Okay, so I need to go because I have a meeting now. Thank you, everyone. I see you next week then.